Water Resources Engineering 2, Unit 1, Gravity Dam. The load combination for design of a gravity dam according to IS 6512/1984. So, gravity dam design should be based on the most adverse load combination A, B, C, D, E, F or G that is given below using the safety factor prescribed. The load combination A, this is the construction condition or reservoir empty condition. So, dam has just completed, but there is no water in the reservoir and no tailwater. Load combination B, that is the normal operating condition, when reservoir is full at full reservoir level FRL and no tailwater, but normal uplift pressure and ice and silt pressure if applicable. Load combination C, so this is the high flood condition. So, reservoir level H, maximum water level, all gates are open, tailwater at downstream flood elevation, normal uplift and silt if applicable. Load combination D, so same as load combination A, but earthquake force are also considered. Load combination E, the same as load combination B, but earthquake force are also considered. However, ice force are not considered. Load combination F, so it is the same as load combination C, but with the extreme uplift force which occurs when drains are inoperative. Load combination G, so it is the same as load combination E, but with the extreme uplift force which occurs when drains are inoperative. So, drains are inoperative, so then here is comes out the full uplift pressure. The criteria for the structural stability of gravity dam. So, this is the mode of failure. So, a gravity dams may fail in the following ways: by overturning about the toe, by crushing, by development of tension causing ultimate failure by crushing, by shear failure called sliding. So, the failure may occur at the foundation plane, that is at the base of the dam, or at any other plane at higher level. So, design shall satisfy or the stability shall be satisfied the following requirements of stability. So, the dams shall be safe against sliding on any plane or the combination of planes within the dam, at the foundation, within the foundation or within the foundation, at the foundation or within the foundation. So, dam shall be safe against overturning at any plane within the dam, at the base or at any plane below the base, and the dam is safe unit stress in the concrete or masonry of the dam or in the foundation material shall not exceed it. So, now this is the some stability criteria. The first mode of failure, that is the overturning. So, if the resultant of all the forces acting on a dam at any of its section passes outside of the toe, the dam shall rotate and overturn about the toe. In that case, the resultant moment at the toe becomes clockwise, means negative. So, if the resultant cuts the base within the body of the dam, there will be no overturning. For stability requirement, the dam must be safe against overturning. So, the factor of safety against overturning is defined as the ratio of righting moment, that is the positive moment. Positive means summation of m r to the overturning moment, that is the negative means summation of m d. So, factor of safety, the ratio of these two. So, moment, all the moments are taken about the toe. So, factor of safety against overturning, the value of this is varies between the 2 to 3. So, then there is no overturning. The second mode of failure, that is the crushing or the compression. So, dam may fails by the failure of its material, that is the compressive stress produced may exceed the allowable stresses and the dam material may get crushed. So, the vertical direct stress distribution at the base is given by the equation, that is the P b direct stress plus minus bending stress. So, this bending stress means the bending moment upon so m upon I into y. So, here this is the dam section with B is the width and consider 1 meter length. So, center and now taking some eccentricity. So, the eccentricity of the resultant from the center of the base. So, the PB means direct stress means vertical force means vertical load divided by the area. So, B into 1 plus minus the moment means summation of B into E moment divided by the I. So, here this is the CG center the axis of the CG that will passes the horizontally. So, then the moment of inertia means 1 into B cube by 12 as well as the y maximum is comes out the B by 2. So, put all the value here. So, means the PB maximum or the minimum the summation of the V upon V summation of the V upon B plus minus summation of the V into E 1 into V square by 6. So, PB maximum that is comes out the summation of the V upon B in bracket of 1 plus 6 E by B. So, this is comes out positive sign is taken. So, then this is the maximum at toe when the reservoir is full condition and minimum taken minus. So, this is the at heel, but if the reservoir is empty. So, then the PB max at the heel summation of the V by B 1 plus 6 E by B. So, then it will change here. So, PB minimum this is the at the toe for the reservoir empty condition summation of the B 1 minus 6 E by B, where this E is the eccentricity of the resultant force from the center of the base and V means summation of the B means vertical force and the V is the base width. So, maximum compressive stress occurs at nearer to the resultant. So, for the safety this should not be greater than the allowable compressive stress F for the foundation material. So, the summation of the PB maximum at the toe this is the summation of the B by B 1 plus 6 E by B. So, that should be less than or equal to the F. If the PB minimum at the heel that will comes to the negative. So, it means the tension will be developed at that point. The third failure mode of failure that is the by tension. So, masonry and concrete gravity dam are usually designed in such a way that no tension is developed anywhere, because these material cannot sustain or cannot withstand to sustain this tensile stress. If subjected to such stresses, these material may finally cracks that can be developed. So, however, for achieving economy in the design of very high gravity dam, the certain amount of tension may be permitted under severest loading or under the burst loading conditions. This may be permitted because of the fact that such burst loading conditions shall occurs only momentarily for a little time and would neither last long nor occurs frequently. So, only for the smaller time that will means burst loading conditions that will be occurs. So, the maximum permissible tensile stresses for the high concrete gravity dam under burst loading conditions may be taken as a 500 kilonewton per meter square. Here is the two cases, the reservoir empty condition and reservoir full condition. So, suppose the reservoir in full condition, so maximum stresses occurs at the toe and the minimum stress occurs at the heel. So, the summation of the B upon B 1 plus 6 E by B. So, now here if the resultant is passes when the eccentricity is less than the B by 6. So, then comes out at the toe means maximum stress and comes out the minimum stress, but the stresses at both the end, that is the compressive stress. But in case of the E is equal to B by 6, so then the PB maximum occurs, that is the twice of the summation of the B by B, and here the minimum stress at the heel, that will be 0. And in case of the suppose E is greater than the B by 6, so then the PB maximum, that is the more stress at the toe, but the negative stresses occurs at the heel. So, then the tension is developed at the heel. Now, suppose when the reservoir is empty condition, so maximum stresses occurs at the heel, okay, and the minimum stresses occurs at the toe. But in case of the E is equal to B by 6, so then maximum stresses, that is the twice times of the summation of the B by B, and minimum, that is the 0. But in case of the E is more than the B by 6, so then the PB maximum, that is the more at the heel, but at the toe, that will comes the negative. So, when the resultant now in full reservoir full condition, the resultant is nearer the toe and hence the maximum compressive stress is produced at the toe when the reservoir full condition. But in case of the reservoir empty condition, the resultant is nearer the heel and hence the maximum compressive stress is produced at the heel. So, reservoir empty with horizontal earthquake waves moving away from the reservoir. Okay. So, now from that here for the no tension in anywhere in the dam, the E should vary the B by 6 from the center towards downstream side when the reservoir full condition, and for in case of the reservoir empty condition. So, this resultant is that will be vary in between of the between from the center to the E is equal to the B by 6. So, then the summation of the B by 6 and B by 6, that will come to the B by 3. So, means the resultant is passes within the middle third, that is known as the middle third rule. So, for the resultant for the eccentricity is less than the B by 6, then there is no tension inside in any of or any section of the any dam section. So, in order to ensure that no tension develop anywhere, so then the PV minimum at the heel, that must be equal to 0. So, if this is the 0, put here the 0, so E comes out the B by 6. So, maximum value of the eccentricity can be permitted on either side from the center that is the B by 6. So, so B by 6 plus B by 6, that is the B by 3, which leads to famous statements, that is the resultant must lie within the middle third portion of the dam. So, for the no tension, the E should be less than or equal to B by 6. If suppose the E is means more than the B by 6, so the tension is developed at the heel. If suppose the tension is developed at the heel, so then the tension cracks will be developed at the heel. So, what is the effect of this tension cracks? Since concrete cannot resist the tension, so a cracks develop at the heel, which modifies the uplift pressure diagram. Due to the tension cracks, the uplift pressure increases in magnitude and net downward vertical force is reduced. So, the resultant force thereby gets further shifted towards the toe, and this leads to further lengthening of the cracks. So, the base width thus goes on reducing and compressive stress on the toe goes on increasing till the toe fails in compression. So, means finally, now here that will compress, finally this will be the if the tension cracks are developed, then it will fail by the compression. And the failure by the sliding. So, sliding or the shear failure will occur when the net horizontal force above any plane in the dam or at the base of the dam exceeds the frictional resistance developed at that level. So, the friction developed between two surfaces is equal to mu times of summation of B, where summation of the B is the algebraic sum of all the vertical forces and mu is the coefficient of friction between the two surfaces. So, for no sliding, the external horizontal force summation of H must be less than the shear resistance, that is the mu times of summation of B. So, the factor of safety against sliding. So, this is the FSS, mu times of summation of the B upon summation of H, and that should be more than 1. In low gravity dams, the safety against sliding should be checked only from the friction. But in high dam, the shear strength of the joint, which is an additional shear resistance, must also be considered. If this shear resistance of the joint is considered, then the equation for factor of safety against sliding, which is measured by shear friction factor SFF. So, this SFF is the ratio of this mu times of summation of the B plus B into Q into 1 upon summation of H. So, where B is the width of the dam at the levels or at the joints, and the Q is the shear strength of the joint, which varies from 1400 kilonewton to 4000 kilonewton per meter square. So, 1400 kilonewton per meter square, that is for the poor rocks, and 4000 kilonewton per meter square, that is for the good rocks. So, thank you very much.